Okay, so today I'm going to start again because last time it was kind of messy, the lecture. So this presentation includes the slides from the previous lecture and also a few more. So so the first slides I'm going a little bit faster, but if you need to ask questions or if you're not following, please just let me know. So as we discussed last time, some logistics, I think you all remember. So the lectures are here, right? So in this classroom. But after that, we can you have with Jan we have the exercise sessions. It's going to be another classroom, but it's right after the lecture. And then you know that every week we are going to assign you an exercise sheet. This is not completely mandatory, but you have this requirement that at least 50% of the exercises have to you have to complete it. Either you upload in Elias, so there is a link there now, or you hand in here during the lecture, or right before starting the lecture with Jan. So you have to hand in the exercises today from the previous lecture. Then I told you that it's really recommended. I strongly recommend you to follow, to try to do all the exercises and also come to the exercise sessions to ask questions. Otherwise, it can accumulate very fast the content, so it's going to be hard to follow up everything that we are planning, that I plan to teach you here. I also told you last time about a test exam, and I would like to ask you if it would be okay to be in this date, so 28th of November. So I mentioned that would be in the end of November. This would be our tentative date. If you are all okay, then we can just fix it as the date. Okay? Not against? It's just the date. Is okay?
Is this the final exam?
No. It's like a test exam, like a practice exam. Yeah, okay. So it's just for you to see how hard can it be. It's usually not hard if you followed the class, all the lectures, and you try to do exercises, and you're if you try to do at least the minimum requirements that I'm asking you to do, then the exam should be easy. But if this is just for you to have a feeling, right?
Does this test exam take the place of the lecture on that Tuesday?
Yes, okay. Exactly. At the same time, it will be exactly. So we are going to mimic the scenario of an exam. So it's going to have 1 hour and a half. That's the duration of the exam. So you have this time to do the entire exam. We are going to grade it. No, we are not going to grade it. But right after, you can come to the exercise session and then see the solution. So you can feel if you could or not pass, if that was a real exam. The final exam will be in a similar flavor.
What about the exercise sheet for that week? Will that be discussed then afterwards?
Yes. So yes, that week.
It's just the week after.
Is it the week after? Yes. All right. So those are just logistics. And then I would just start again. So imagine that we just met. And usually I start with this. So everyone asks me, why causality? We have a lot of breakthroughs in AI. It seems like everything is solved. There's nothing else to do. Right, so we have, for example, many systems that can do predictions or make predictions extremely well, especially in high-dimensional settings. So usually we have examples in reinforcement learning, computer vision, natural language processing. So you are all used to see these keywords with several breakthroughs and huge progresses in this field. As an example, we have, for example, the deep AI, DeepMind AI beats world's best Go player in. This was the AlphaGo, right? So it was a few years ago, 2017. This news. We have also cars that can. It's fully autonomous cars, so also AI, so fully controlled by AI. we have AI systems that are better than human doctors for predicting diseases. And you all also probably have heard about the GPT that is at the same time exciting and scary, because the outputs is really impressive, and it seems like we are close to having some type of human intelligence in these AI systems. But what do you think about this question? Do you think that we are done? There's nothing else? What are the challenges that are still ongoing here?
I think AI is not necessarily reliable in settings that need security, for example, for tasks. So like it's more of an approximation or like a heuristic sometimes, or it feels like. And often AI is like a black box, so you can't see what is actually happening behind the scenes and understand the topic that you're facing. So you can't see like the connections that are there in reality that make this or that form the way AI interacts with it.
Exactly. So this is something that we call explainability, and because we don't have explainability, usually we don't trust on what the algorithm is doing. Is it fair according to the society? Is actually getting the expected solution for the system, or is just guessing? And this is just a coincidence that's getting a good prediction. So there are actually many challenges, and this is exactly the first topic that I picked, that's about explainability. So even though we have systems that can do prediction in human medicine, for example, we cannot learn from it. We cannot accept the solution and then extrapolate and then create treatments for it, or we usually have a way to to make decisions about what actually we cannot learn about what can be done after seeing this output of this algorithm. The second one is about fairness, is just an example of explainability as well, because if you don't know if certain decisions are biased towards some types of groups of people, or you don't really know if sometimes you have unbalanced data, maybe the predictions are just maximizing the accuracy, and this can just be done by choosing one specific type or group of people. So you can just instead of getting exactly the real features of the problem, so for example a disease, instead of getting features related to the disease, you can actually make predictions taking into account features of people, so race, age, and stuff that don't really matters about the disease. And explainability would help us to actually design a more fair system, right? So when we try to understand the reasons about what's happening there, why a decision is being made, or is this actually fair or not? All these type of questions, they are related to consequence, so cause and effect relationships. And detecting cause and effect relationships is one of the biggest challenges in AI. So we don't know, in most of the deep learning algorithms or machine learning algorithms, they are not able of actually grasping causal and effect relationships, and that's why the field is important, and it would be helpful in the next generation of the algorithms, I would say. Questions related to this? So who have heard about Udea Pro? 2, 3. So Udea Pro is, I would say, not the father of causality, but it was the one that actually made the field more accessible or more transparent, and actually help us to apply causality in the empirical sciences. And he actually wrote this book of causality. So I would recommend this to have like as a reference for this course or for your entire career if you are planning to apply causality in your data analysis. So currently he's the director of the Cognitive Systems Laboratory at the University of California in Los Angeles. And he won the Turing Award in 2011. So that was exactly due to the fundamentals contributions to artificial intelligence through the development of a calculus for probabilistic and causal reasoning. So in this lecture, we are actually going to see this calculus and this probabilistic and causal reasoning tools that he developed. And I actually like this quote of the Book of Why, that he also wrote the Book of Why. It's a nice book for you to have to get an introduction about the field, and it says the following: deep learning has instead given us machines with truly impressive abilities, but no intelligence. That's what I was trying to explain before. So those capabilities, those predictive capabilities, they seem like a human intelligence, but it's not exactly as human intelligence. And the difference between having capabilities, these impressive abilities, and intelligence, this difference is profound and lies in the absence of a model of reality. So the fact that deep learning or these artificial intelligence algorithms are agnostic, right, or it doesn't take into account of the real model behind, or the model that generated the data, or the reality behind these data sets, is exactly what prevents these algorithms to not having human intelligence, or intelligence as we are used to see as humans. So that sentence, that quote actually, it's summarizing the whole idea of causality, because to have causality, you need some information about the underlying model. And we are going to see how to learn a little bit about this. So as I said, Pearl was not the father, so that's a very old theory. So it started, I would say that these are the two main names in causality. So Guido Imbens and Joshua Engrest. So the first is a professor of applied econometry in the Stanford University. And he wrote this book here, Causal Inference for Statistics, Social and Biomedical Sciences. So a question, who have heard about the potential outcome framework? Okay, so that's another framework that also deals with causality. It's very popular in the economics in general, and it's really old, like from the 50s. However, the notation, so although they are equivalent, so Pearl actually show an equivalence between both frameworks. Most of the applied causality that you're going to see in these days are either from economics or from human medicine, and using the potential outcome framework. The difference between the two frameworks, so although they are equivalent, is because the difference is because the language is due to the language that the potential outcome framework uses. Is very counterintuitive, so it's not really transparent. So I would say that the advantage of the Pearl's framework is that it brings some language, so it's the graphical language, so through the use of graphs, it helps us to understand what's actually going on. So you have a nice view of the reality, and this helps us to understand what are the assumptions behind the analysis. Many times when you see the applications of the potential outcome framework, you don't really understand what the assumptions mean. I can give you some examples later. But this framework, we are going to see maybe in the last lectures, we are going to see a bit of it. It's equivalent to the Pearl's causality framework. So Joshua Engrest is another professor of economics in the MIT. And he wrote, so that's another famous book, Mastering Metrics. And both of them, actually, they won the Nobel Prize in Economics for their methodological contributions to the analysis of causal relationships. So you see that it's really recent and really popular. So this is in 2021. So it's everyone is really excited about causality. So even though the potential outcome framework is started in the 50s, right now causality is getting a lot of popular. Is becoming very popular because of this idea of explainability. So deep learning actually brought us a lot of advances, but we are stuck right now. We don't know what else we can do. So without explainability, we kind of cannot, we are stuck, right? We cannot do anything more. We want actually to use this to make decisions, to create treatments, to apply, to propose some interventions in the reality. So actually we can change the reality and see that effect in reality. Yeah. Questions? No. Who have heard about Yoshua Bengio? So he was the father of deep learning. You should know this. So he's really active in deep learning. So he actually also, so right now he's a professor of the University of Montreal. He's also the founder of MILA in Quebec. It's the Quebec AI Institute. And he won, together with Geoffrey Hinton and Ian LeCun, he won the Turing Award. So this is the computer science Nobel Prize for actually developing deep learning, right? So for conceptual and engineering breakthroughs that have made deep neural networks a critical component of computing. The year is 2018, so not so long time ago. And he's actually a lot of his recent work is related to causality as well. So this is a quote that he gave to this interview of the IEEE Spectrum magazine. He said that causality is very important for the next steps of progress of machine learning. So he is starting right now, I would say 2 or 3 years ago, working with causality. So he's not as experienced as Pearl, for example. Pearl is now 20 years working on the field. But he notes exactly because he is in the deep learning field, he notes that this is exactly the component that's missing to go to the next generation of the AI algorithms to achieve the explainability that's missing. So if you are interested in this, you need to learn causality. So that's the summary of this these quotes here. So why causality is so important? And so in the end, there are a few capabilities that we can list here. So the first one is explainability. So provides a better understanding of the underlying mechanisms. So we don't want to use these systems not only to do the predictions in a blind way. We want to understand the mechanisms through these outcomes, right? And this can actually be done through some type of algorithms that we are going to learn in this course. That's called causal discovery. So these causal discovery algorithms, they can use data and learn some pieces of information related to the underlying causal mechanisms. So you're going to learn, so causal discovery, you're going to discover a few, some pieces of information of this underlying model. Then you can also estimate or infer causal effects. So what's the difference? So in the previous lecture, we tried to see the difference between just doing prediction and estimating effects of interventions. So a causal effect would be the effect of an unrealized intervention. So I don't want to go there in the system, perform an intervention and see what's going to happen later. I want to imagine. So it's a hypothetical intervention. So what would happen if I went there and make the intervention? What would be then the effect? So this can be estimated completely in a data-driven way. We are going to see also this in this course. And this effect is not exactly the same as a statistical association or correlation. So we can distinguish the difference between the effect of an intervention, as if it was actually happening in the role, and the usual correlation that we can detect from data. So there are two techniques that allow us to do this. The first one is called causal effect identification. So there are tools you are going to learn in this course, causal effect identification tools. And then later, from a formula, you can estimate so causal effect identification just provides you a formula in terms of the probability distributions, but you can use data to estimate these probability distributions and then get the estimated effect. Fairness, we discussed this already, so it's a type of explainability that we can have. Another topic that I won't cover in this course, but if you are interested, we can discuss offline. That's about generalizability. So when you compute a causal effect, either through observational data or through an experiment, you usually are assuming that the data that you have available, for example, imagine that you run a clinical trial here in Germany. This is not exactly immediately transportable to other countries, for example, the US. So transporting a causal effect that you observed in a specific population is what we call generalizability or transportability. So there are techniques that are using also the language of causality that by understanding the difference between the domains, you can transport a causal effect from one domain to another. And domains here can be anything, can be different species, can be different populations, can be anything. But of course, you need to know more about the differences or the invariances across all these domains to do this in a proper way. And finally, data fusion is something else that causality is touching. So data fusion allows you to combine different data sets. So imagine that you have data from one population, or that it was through some experiments. So they are not exactly over the same set of variables. So they are very heterogeneous. And the proper way to combine these data sets, you also need to use the language of causality. I don't think I will touch on this, but it's the same case as before. If you are interested, we can discuss. I can give you some pointers on how to learn this, or even maybe I can prepare some extra lectures about this if you're really interested in this. So that's actually the big picture of all the topics that we can do with causality. I'm going to cover a lot, the first and the second, about explainability through causal discovery, and second, how to estimate a causal effect. So we have identification first and then estimation later. So we are going to learn these three topics. So causal data science has these three goals, as I mentioned. And I like to recommend this paper, Causal Inference in the Data Fusion Problem. It's a paper by Elias Barenboim and Yudea Pro. And it actually covers all these tasks that I just mentioned. So if you want to read more, I really recommend. It's a very short paper. You can read it. You can see some technical words. You can see other reference related to these topics. And also, that is this website that I also recommend you to do, to sign, to register on this, is a web application. So you can use your academia email. You can just sign up here. And then you have a whole interface allowing you to compute causal effects. So you don't have actually causal discovery there, but you can draw your own causal diagram. You can compute the effects and estimate the effects. It's really nice. So even for our exercises here, you can use this website. Of course, in the exercise sheet, you need to show how to do it. You cannot just say, I use the website and that's the answer. But I recommend you to use so you can learn, you can create your own examples and see how it goes and see if the effect is identifiable and so on. So I recommend it for learning. So there are 3 books that I would recommend you to read, not completely, but so the book of why you can read completely. So it's a short book. it's more introductory. I'm going to follow the first 3 chapters of this book. So there are 4 chapters here. The 4th chapter, if I have time, I'm going to cover as well. So this will you make the whole book. It's very short, so you would be able to learn this in a lecture, as in a class, as we are planning here. But it's too short, so I'm not going to cover just that. So I'm going to cover causal discovery, which is not it is not covered in this book. Also, this book doesn't cover causal discovery. But everything that's here, you should be able to know. It's a very easy book. This one is hard to learn, so I would just have it for reference. So I read many of the chapters, but usually to actually learn, you need to use the references of it. So it's just a reference book, right? So you don't learn from it. You can have a superficial view of the topic here, but to actually understand, you usually go to the papers and then you learn from the papers. But I like to give these 3 books as pointers for causality. They are the most important ones. And related to this book that I'm following, that is also a website. It has a similar flavor, but it's open, so you don't need to register here. But all the exercises of this book, you can also solve it through this web application. So the website is causality101.net. So both of these web applications were developed in the Causal AI Lab by Elias Barenboim at Columbia University. And it's free for anyone that's learning, right? So you don't need to pay or everything. So you can actually follow the exercise of this book in this website. Yeah. So I want to now start a little bit more about, actually this was covered in the previous lecture, but I'm going to show you the graphs and maybe you can ask questions. Up to now, do you have questions? Okay. Okay, so that's the example of the firefighters, and I'm going just to show you, since we explained this already, I explained this already in the previous lecture, I'm just showing really quickly what's the goal here. So the idea is, can we guess what's the size of how severe is a fire just by observing the number of firefighters? Every time that we have a correlation, so this is a case where obviously we have a correlation. You can plot here, you can have a line, it's a positive correlation. The fact here is that X helps to predict the probability of Y. So every time that the probability of Y given X is different than just the probability of Y, this means that having information about X helps you to predict the Y. So that's why it's a good predictor. And being a good predictor helps us to do prediction, right? So pretty obvious. But this is really completely different from using X to change the value of Y. If I change the value of X, I cannot expect a change in the value of Y. This would be, so that was the question before, right? So we can guess what's the severity of the fire by observing the number of firefighters. So I can, so the severity increases with the number. So I can guess by looking at the number, I can guess how serious was the fire when it started. But can I actually use this information to make a decision to change the reality, right? Then that's the question. Should we decrease the number of firefighters to reduce the fire, since that's actually what the prediction actually told us? And of course not, right? So why not? And to answer this question, we need to know what's the causal effect. So causal effect is different than statistical associations. So that's actually is the definition of a causal effect. It's not that formal, so it's just a first introduction about what a causal effect is. But a causal effect of a variable X on a variable Y is just a quantity. Doesn't matter what's this quantity, but it's a quantity that tells us how much Y changes after an intervention. And doing this intervention, we need to define as a hypothetical intervention, as if I was there in the environment changing the value of X, and then after the intervention observing the value of Y. And this intervention is actually denoted. So this is the notation that we use in the field. So that's the formal notation of a hypothetical intervention. That's do, the operator do. And you put inside here what you are doing, which is changing the value, the variable x, to a fixed number small x. So you are setting the x. X is no longer a random variable here. It's a constant. After setting x is equal to a small x, what would be, for example, it's a quantity that's derived that tell us this change on y. So what would be, for example, the expected value of y after this intervention? And this quantity, we can compute it. That's what we are going to see. So this you allow us to answer this question. So if a different number of firefighters were dispatched, so in the beginning there was a fire, then a different number of firefighters were dispatched. So we are changing the do. X is equal to, it represents the number of firefighters. Now we fix to a certain number. Would this change the initial severity of the fire, the expected severity of the initial fire?
No.
No, right? So why not? Why you know this?
We know it because from the real life we know that the fire, we send more firemen if the fire is big. So changing the number of firemen doesn't change the fire.
But you know how a fire is created, right? So
Yeah.
you know what's the mechanisms of generating fire.
Yeah.
And definitely it's not the firefighters that are putting fire in the forest or something like this. So since you know a little bit about the underlying model, you know how to reason about it. So you're not just bringing data to answer this question. You are bringing your experience on the reality. And that's why causal effect is actually defined as the effect of an intervention. So you would imagine going there, changing the number of firefighters, and then seeing what would happen with the fire. This quantity here, expectation of y given to x, it's an expectation, right? So it's in the same sense of expected values from distributions that you have seen before. So you compute it given a probability distribution. And this distribution is now a different distribution because it's a distribution of the data after an intervention. You would actually be able to obtain this distribution if you went there in the environment, performed an intervention, and collected data after it. This would actually give you the probability of the y given to x. And this probability is denoted by probability of y given to x and referred as interventional distribution. So we're going to see a lot of these names here. So our goal is to recover this probability of y given to x without actually intervening on the system. How can you do this? So this question can actually be answered if you have some type of knowledge about the underlying system. So in this example of the firefighters, we don't need to know a lot. We just know that the variable x, which is the number of firefighters in action, is a function of the fire, not the other way around. So you dispatch the number of firefighters depending on how serious was the fire, right? And the fire is a function of this variable u that we are just assuming that there are other factors that are creating the fire. So we are just denoting it as u, y. And I don't know what's the function. I don't know what's the probability of y. I don't know anything. But I know for sure that that's the order, that x depends on y and something else, but the y doesn't depend on x. And because of this, I can say that y is not a function of x, which means that x is not a cause of y. And because of that, I know that the expectation of y given to x is exactly the expectation of y. So if I change or not the number of firefighters, won't change my y, won't change the size of the fire. So this equality here, for every x, so it doesn't matter the x that I set here, this equality means that x doesn't help to predict y, in the sense that the intervention, I think I wrote here, the intervention do x is independent of y. So we are talking about a function of a random variable, which they do, and this function is independent of y. So it has a similar sense as probability as before, but now we need to account for these hypothetical interventions that we are trying to deal with. I will give a pause later in 20 minutes, so you can go to the bathroom and so on. But let me just finish this first part. So I told you that randomized experiments actually give you access to the experimental or this interventional distribution, right? So what actually happens here? So I'm giving you notation of causal diagrams, but you don't need to know right now. I'm going to define later what's a causal diagram. But what actually happens? So in the previous lecture, someone actually, I don't remember who, was asking about confounding. So it doesn't matter that you are actually going to the environment and actually performing an intervention. Sometimes you are still having influence of other confounders, and this can actually bias your the outcome of this experiment. So that's why I wrote here a perfectly realized randomized control trial. So if you actually controlled, so you got, for example, a completely random for a sample of a population. So this population is not biased anyways. And everything that was not randomized was controlled in the sense that it was fixed. So you are in a perfect scenario. What's happening here is that the effect of we are randomizing the assignment, right? So we have, for example, a binary variable x. This, for example, is a treatment, can be a placebo and a medication. And in one group, we do this x0 could be the placebo. In one group, so we divide the sample in two groups. So this sample is really randomized. So the fact that it's randomized, we are not, the function x, so this, the assignment here, so the fact that I'm giving the placebo to this population is not because this group because this group has some particular characteristics. No, I'm just randomly getting people and getting the placebo to them. And because this is random, no function here that was, no variable that was affecting the assignment of the x is, no function, no, I'm kind of minimizing the effect of these other factors that are making me to assign the placebo to these people. So in a perfect scenario, there's nothing actually affecting the assignment of x. And this randomization is, if it's really well done, it's removing any confounding which is represented by this dashed variable here. So if I do this for the placebo and I do the same for the medication, the only statistical association or correlation that's left between x and y has to be due to the variable x, because the only thing that I'm allowing to happen here is what happened after getting the medication to these people, right? So everything that was before, which was represented by this dashed line here, was removed by randomization. I'm removing, so I'm minimizing this effect. So that's why in the end, if I get what's the expected value of y, for example, the disease was cured or not in this group. If I get the expectation of getting, of how well the person is after taking the placebo versus how well they are now after taking the real medication, this difference is actually the causal effect, because there's nothing else that's making the association between x and y. Yes.
In real life examples, if we you try to use a uniform distribution as randomized, or do you try to mirror the original distribution? For example, if you had like a group of people, there would be different people of different ages, right? But there are more people that are older than young people right now, for example, in the country. So would you try to mirror that, or would you try to have a uniform distribution of all ages?
You need
I think the problem of that example is that you don't have control over the age, so that's a variable that developed over the time they are alive. So I think this scenario applies to, you give one group a medication and the other one a placebo, but the age of the people you have in a study, you can't control that. It's just you can't change that.
Yeah, so the idea would be that in the group of the placebo and the group of the medication have the same distribution of age. So you would have both kids and elderly people in this group receiving placebo and also in the other, because you don't want the age being affecting it. So, but the question that you asked me is actually related to the idea of generalizability. So because if you are in a population that is very old, let's take Germany as an example. So you have more people that are older than people that are young. And if you get a random sample of Germans here or people that are living in Germany, you have a higher chance of getting more old people than young people. But then the causal effect that we're going to have in the end is a causal effect that has internal validity. This means that for populations, for the Germany population, this effect is not biased. However, if you transport to another population, for example, Brazil, where there are more young people, then you have a bias because there is a difference in the distribution of age. And this difference actually biases the causal effect. So if the drug developed in Germany not necessarily has the same effect in Brazil, in people in Brazil, because of this difference, at least not in the expectation, right? So you need to change. So there is a formula to like a weight for the age distribution in Brazil, something like this. So that is a way, and this is dealt in the transportability theory. By knowing that these two countries are different in the age distribution, you know how to transport one effect from one to another.
Okay, I understand. So it doesn't matter how we distribute it, but because we're comparing distributions, the distributions have to be the same.
In both groups, you want like
the same
some homogeneity.
And the distribution doesn't really matter that much more than the comparability.
It matters for external validity, but for internal validity, no. That's why also when we start learning about transportability, we have this take-out message saying that even for randomized control trials, causality theory is essential. So it's not actually the golden, everyone says randomized control trials is the gold standard of causality, and it's not. It can be if it's perfectly done and only for internal validity, but not for external validity or different things.
Yes, okay.
So yeah, so randomized experiments actually can give us this difference, and this difference is called average causal effect. Sometimes we use ACE or average treatment effect if this is a treatment, ATE. So you probably you see this name many times in the literature. So I'm going to skip this data analysis thing that we did last time, but basically I showed you that you can actually have the probabilities. This actually is covered in the exercise sheet for next week, not exactly these tables, but you can have examples where the probabilities flip. So for example, in this example, we have the probability of y given x equals to a. So we have a drug A here is higher than the probability of y given x equals to b. So it seems like the treatment A has a better success rate than the drug B. But if you actually do a different type of analysis, for example, adjusting for some covariates, you can flip the result. So now we have that the drug B seems to have a better success rate than the drug A. So those tables are called, so this type of results is called Simpson's paradox. So I don't know if you remember from previous lecture, but it only happens because you don't know what's the underlying mechanisms. So since you don't know if this S here that S is the size of the stones, kidney stones, you don't know that this was actually a confounder of their relationship. You have to know that this is a confounder to adjust for it and then get an unbiased estimate. And the one that we are seeing here that adjusting for S is the one that's related to the causal effect. So the causal effect is after adjusting the covariates. But you need to know what's the underlying system to decide which type of analysis we have to do. And this is just an example, don't need to worry. We will see how to know what's the analysis that you want to do for every data set that we will have later. So that was the example of confounding, right? Where confounding is defined as like this. So a causal effect on X on Y is said to be confounded every time that the probability of Y given to X is different than just the probability of Y given X. So you cannot just do a simple statistical association, marginal association, for example, to get the effect of X on Y. This would be different, so the results will be different. So every time that there is this difference, we say that there is a confounding, and this has to be adjusted for. Okay. The other type of, if I'm going too fast, you can tell me, right? That was the second paradox that I explained last time. That's the Bergson paradox. That's the opposite. So now we are conditioning on some variable, and this is wrong, right? So this is the case where S was the type of hospital that we had there. And when I generated this data, I generated this being a hospital that were both, and last time I told you differently, but I checked there in the code later. We had like some issues with the number, I don't know if you remember, but I checked it later. Actually, the location 1 is both for mental disease and also cardiovascular disease. So it was specialized for this. So if a patient goes in this hospital and doesn't have, for example, mental disease, whatever, so the chance of having the other one, because it was specialized in this other disease, is much higher, because it's either one or the other. So it's a function of both. And this type of, we are going to see later, this is called collider. So the variable hospital is a function of both mental disease and also cardiovascular disease. So it's a common effect of two variables. And this formation is going to be called collider. We are going to see later. And this paradox is also called collider bias. So conditioning on collider is always wrong. Not always. There are cases where it's essential, as long as it's essential to, if it's not essential to condition on a collider, then you're doing wrong. We will see this later as well. Yeah, so that's exactly this slide here about spurious association, which is created by conditioning on site. And then in the case, the causal effect here is exactly the marginal, is exactly the conditional expectation of Y given X. So you don't need to adjust by anything here. So just getting the simple correlation between X and Y gives you the causal effect. In this case, it's 0. In this example, this is going to happen because they are independent in the beginning. But this would be the formula to compute the causal effect in this example, and then you would observe that they are completely independent.
I have a question. So X is if they have a cardiovascular disease or not. What does do X equals X imply here?
So it's changing. So that's also causality is important. There are many scenarios where you don't do the randomized experiment because it's unethical. So in this case, it's actually giving you cardiovascular disease. So I cannot do it. So imagine doing a randomized experiment for this. So causality from observational studies is really important for this type of examples. Right? Okay.
Yes.
So this Pearl's causal hierarchy, it's also called Pearl's ladder of causation. If you read the book of Y, you maybe heard about it. But it defines 3 different layers of inferences. So there are actually 3 types of inferences that you can do. And that's a way to define them. So this is a picture from the book of Y, and we have, so it's a ladder, right? So with 3 rungs, and we have 3 different rungs, so 3 layers here. So the first one, it's called seeing, or for observations, right? And the type of analysis or data analysis is the one that we are used to do. So here we are interested on simple associations or statistical associations between variables, random variables. And everything that you learned in AI or machine learning that allow you to do predictions, right? So all these predictive models, they use associations to do this. So by knowing or by estimating the probability of y given x, you are able to predict the value of x given the values of x, predicting the value of y given some of the values of x. So classification, for example, you can predict what's the class 1 or 0 given some features. Or regression, you can predict what's the value of y after conditioning or the covariates that you did there. So decision trees, deep neural networks, everything that you basically do for doing use for prediction, the reasoning behind this is to get the most, as to estimate this in the best way that you can, right? So it allows you to answer this type of questions. What if I see, or how would seeing X change my belief in Y? So you see here that it's seeing is the verb that I'm using. So after observing the number of firefighters there, what can this tell me about the fire that started? I'm not trying to change anything. It's just guessing. It's a different type of game. So what does a symptom tell us about a disease? So I'm observing some symptoms and then I can guess which the disease you are having. This is completely different from questions in the second rung, which is about doing, right? So the second one is about interventions. And this requires a different type of distribution, which is the one that we just discussed. So it's the interventional distribution where we have the do X here. So after performing an intervention on X, what's the probability of Y? And I can even consider some covariates, like some conditional terms or variables after the do. So for a specific group of people with age between 20 and 30, for female, and I mean, you can have a lot of C here. But what would be the expected value of Y after doing an intervention on X for these particular people? Techniques actually for answering this question, there are some that you have heard about. Reinforcement learning, as long as this is like a online reinforcement learning, where you can access the environment and you do the intervention and then you observe later, can do this. Any other method that you know, so this, I wouldn't say that this is actually causal, because in the end they are assuming that the Markov decision process that you are estimating there is the true one. So I would say that this, people kind of say that this is in the causality framework, but that is the assumption that this is the real one. This is the real process behind the data generating process. It's a strong assumption. I mean, in causality, sometimes we can use the causal graph as being the assumption behind it. So it's again a strong assumption. So you have to know what's the structure of the model to then do causality. So you're assuming some type of model behind it. But that's the point. Either you assume that the model is known and then you estimate what's the causal effect, or you have access to the data, to the environment, and then you can access the output of these experiments. And this would allow us to answer this type of questions. What if I do X, or what if I perform an intervention on X? What would be the value of Y if I intervene on X? Or will my headache be cured if I take an aspirin? So you see that now I have an action. It's first I take an aspirin, and then I want to know what is going to happen. So it's different than before. And the third layer is the hardest one because is regarding to imagination or retrospective thinking that's called counterfactual. So people also say that this is related to an individual analysis, and this notation is the notation of the potential outcome framework, but I can explain to you. Basically, it's saying the following: what is the probability of Y after doing an intervention on X? But I know that this person actually received the treatment X prime in reality, and also the outcome of it was Y prime. So for example, I have a person that took an aspirin and then the headache was not cured. So I took an aspirin X prime and the headache was not cured. I want to know what's the probability of getting cured if the person doesn't take the aspirin. So it's the opposite. So I know what happened with a person. I want to go back in time and know what would happen to the same person. So it's an individual level analysis. What would happen with the same person if he or her she did something differently? What would be the outcome of it? So there's much more information that you need to know here, because you need to take into account the the intrinsic characteristics of this person, right? And to really know that, you would have to go into the full specification of the data generating model, which is the structure causal model. There are a few cases where you can actually estimate this, but these assumptions are usually very strong. But I mean, people, I would say that the field is really in a delicate situation right now. Many people are estimating counterfactuals. So if you go to Google Scholar, you see a bunch of people estimating counterfactuals. But in reality, they are making some assumptions. Sometimes they even don't specify what are assumptions that they are doing there. But I mean, I try to cover at least a few types of analysis where we can estimate counterfactuals from data. Yeah.
So it's like if I eat cake and I'm happy, then it's like thinking about if I didn't eat cake, would I still be happy, or how would I feel, for example?
Sorry, can you repeat that?
So this counterfactual thing is like,
yeah.
If I eat cake and I'm happy, I would think about if I didn't eat cake, how would I feel?
Yes, something like this.
And
it's more personal, right? So you're taking into account something more than just the expected value of a population. So you're not just constraining the population to those people that are really similar to you, and then seeing the average effect for this very small group of people, which would be conditional causal effect. Like here, it's really going into the individual. And to know this, you would need like the arrow terms of the model, like something that's stochastic, like you don't know this, right? So either you really know the model, or you are making very strong assumptions there.
And the x and y's, or the x prime and the y primes, would, for example, be the amount of sugar in the cake.
Different levels of the same variable. So for example, x without the prime could be a level of sugar, and the x prime would be a different level of sugar, right?
Okay.
Or how big your slice of cake is, I guess.
Oh,
Yeah, or something like this.
Is that also like saying, oh, if I studied more, I would have passed the exam?
Yes.
Okay.
So there are some analyses that take, like, people that studied 20 hours a week pass the exam, but this is not talking about you, right? Because it has to consider your experience, your life, your difficulties, and a lot of things. Okay. Okay, and what is the challenge of this type of analysis? Exactly crossing over, right? So usually you are in one level of the ladder. For example, you are in the first level or the first rung of the ladder, where you just have observational data. I didn't perform an intervention. I don't know the model. I don't know anything. I just have data. I'm the first layer of this hierarchy. But I want to do more. I want to infer causality. I want to infer counterfactuals. So how can I move up in this ladder? That's the challenge. That is a theorem that's proved. I give a reference. I think I forgot to give the reference in the end, but I can give a reference later. That tells the following. To answer questions in a specific layer I, right, I need information from that specific layer or higher. So I cannot infer causal effects, or to be more precise, I cannot infer the entire causal model just from data. I can infer pieces of information and sometimes one particular causal effect, but I don't have the guarantee that I will have any causal effect of interest in the end from a data-driven analysis. So either you give me prior knowledge from experts, or like you can draw me the structure of the diagram, like the diagram representing the structure of the model, or you can provide me the topological order of this, the variables, right? So which variable comes first? Sometimes you can say that's more, there's something called the conditioning inaudibility from potential outcome that says this set of variables are exactly removing my confounding. It's very strong, but some people use this. So you need something more related to the underlying model to infer causality. And over this course, I'm going to provide you with tools that are going to allow you to do a completely data-driven analysis. So from causal discovery, you can learn some pieces of information. So you are going to be unable to learn the full causal model, but you're going to learn pieces of it. And then you have identifiability tools to know if this information that you just learned is sufficient or not. It's possible to be no, the answer, and then you're doomed. So you need more data, you need more variables or something like this. But then if you are lucky and it's identifiable, then you can estimate using the data that you provide me. So it's not a limitation, my limitation or limitation to the field. It's a theorem that tells you that's impossible. And I think I have time. Before that, let's just read this. I want to see the answer for the question later. So let's just read together. Another huge study found no evidence that cell phones cause cancer. Okay? Then the guy says, what was the WHO thinking? Then the other guy says, I think they just got it backward. Huh? Well, take a look. Then there is this graph here that shows in 1970 it starts like increasing the total cancer incidence. So the incidence of cancer is growing very fast. And then 10 years later, the cell phone users started increasing as well. So it seems like cancer is causing cell phone users, because first comes the incidence of cancer and then the cell phone. And then the guy says, no, you are not. There are so many problems with that. Then the guy says, just to be safe, until I see more data, I'm going to assume cancer causes cell phones. Then my question is, do you think they are going to be able to decide which causes what just by seeing more data? What do you think?
I think we will, otherwise we'd be kind of doomed if we couldn't decide such a problem.
Yeah, the problem is this question is ill-formed. You need a very specific type of data. So you need data from confounders, you need data, maybe experimental data, you need other type of data, but just data from either cancer incidence or cell phone users, just these two variables, Doesn't matter if you're just collecting more and more data over the years, you will be always seeing the same correlation between X and Y. You will never be able to decide which causes what. But if you are able sometimes of collecting other variables, and then these other variables explain why these variables are correlated, maybe then they are going to be able, through this causal analysis that we're going to see, right? So just seeing more data, it's hard to explain if this is true or not. That's fine, I have better here. Yeah, so I want to formalize a bit more about what are this underlying causal model and also the causal diagram, and then I think you'll be able, at least with this, to do a few, to complete the exercise sheet of this week. So the causal model is kind of simple. Basically, that's the definition. So it's a tuple, so there is 4 elements in my tuple here. So the first is a set of variables that is usually denoted as V. So every time that you see a V in this course is because the variable is in this set here, so V1, Vn. So all the variables that are in set V, they are going to be called endogenous or observable. So I observed, so I collected data about these variables, right? So I have access to it, and I have my data set, I have columns with values of it. However, the data doesn't depend on only the variables that I was able to collect. There are many other factors in the world that are explaining my variables V, right? So suppose that V is a disease, and I collected data about a person having or not having this disease, but this is not sufficient for understanding if the person would have this disease or not, right? So the fact of the person has the disease depends on other comorbidities, depends on the age, it depends on many other factors. And if those variables were not observable, are not in your data set, then they are going to be in the set U. So U are the variables that are called exogenous because they are just outside of your data set, or they are not observable. Then we are going to have this F. F is just a collection of functions. So every function in this collection of functions represents the mechanism of generating one of the variables of the set V, right? So, for example, the V1 is a function, F1, that depends on some variables that we are going to call them as PAI, or parents. So PA from parents. So those are the causes, because they are arguments of these functions. So PI is a cause of VI and is part of the set V. So they are the observable causes. So all the arguments that are observable are going to be called parents. And every other variable that's argument of this function, but it's not observable, is going to be part of the set U, right? This other variable, the set of variables here. Okay, so just this. So every variable Vi is determined by a function that depends on the parents, which are the causes that are observable, and the other variables that are not observable. That's what's explained in the end here. And to complete, actually, I need the probability of U. So usually this is not a deterministic model. I have U's that are random variables. So all these variables, so you could actually transform all these variables into random variables. They are all random variables, right? But this U's, I need at least a probability distribution. So if you have this, you have everything. You can.
This UI in this as a function of UI shouldn't be capital, like.
Sorry.
I think it's small UI element of big UI, which is a subset of U.
This UI should be bold. Yeah, I think it is bold, right? I don't know. Sorry.
They're the same.
No, the U variable is the entire set of U. But the UI is another set of variables,
Yes.
but they are only the variables that are argument of the function of Vi.
UI in this function is the same as UI, which is subset of U. Yes, these are the same.
Yes.
Yes, so, but this is the value of it. So that's the notation that we usually use. Bold are usually for sets of variables. So this should be bold. I think it's just the weird notation here. But this is a set, so it should be bold. Capital letters are for random variables and sets. And the small, so the same letter but small, is just the value of the random variable, right? So that's the value of the variable vi. Okay.
So it's the set of the value of that random value, because that's a set of.
Yeah, set of variables. Vi is just one variable
Yes.
there,
UI
but this is a set of
set
variables.
of values.
Yes.
Yeah. Okay.
Could be a set as well if you want.
Yeah.
So it doesn't matter in this case if it's capital or not.
There.
Yeah.
Yeah, here I'm defining variables, so matters, right? So I don't want the specific value. So one random variable can take different values. This is the one specific value that the set UI can have, right? So when usually we have the probability, so that's kind of the notation. I don't know if you are used to it. So probability of y given x is actually short for this. Okay. So yeah, if you write like this, implicitly I'm just saying that for whatever y I'm taking here. So many times that you're going to see this in this course, because I use the short notation for this. But if I'm using the capital letter here, it's because I'm considering the distribution for the random variables at any point, right? And this is just for one value specifically. This one is for one value specifically. Okay. Yeah, one assumption that we have here in the lecture, and because this is also a assumption in, I would say 99% of the field, is that there is no feedback loop or cycles. So you see here that there is an order. So a variable v, can only be created by variables that are already defined before. I cannot have cycles. I cannot have a system of differential equations, for example, so where you would actually model some feedback loop or stuff like this. So there is actually ongoing research on this in the causality field, but I'm not going to cover this in this lecture. This would be very advanced. Although the algorithms, I'll tell you every time that the algorithm is kind of covering part of the cycles of the theory. For example, the causal discovery algorithm that I'm going to teach you, that is a way to explain the modules that's inside of the representation that it's learning that can also have cycles. I don't know if I will have time to actually explain how to detect this, but it's important for you to know that I'm going to teach you the most flexible algorithm that exists, because it's one that doesn't assume anything doesn't assume many of the strong assumptions that are common in the field, and also it's the one that people are actually researching on right now, for example, for recovering cycles.
So would a cyclic mechanism mean like V1 is dependent on V2, but at the same time V2 is dependent on V1?
Yes.
Okay.
So in statistics we call this recursive models. Don't know if you have it.
I have a question.
Yes.
Regarding the previous slide. It says that PAIs are of V, but so the dependency is like, but the VIs are dependent on the PAIs, right?
So the dependence, so associations, you're going to see association between both.
Yes. So VI is dependent on F, and F is dependent on PAI.
Now, F is a function. So VI is a function of the parents, which are other variables. So you're going to see dependence here. So VI depends on the parents.
But the parents are part of the V's too, right?
Yes, but in this you cannot have the same. So I cannot depend on myself. There's no self-look,
Okay.
and the order that exists is an order to create the variables, in the sense that I would never depend on a variable that was not defined before.
So one of the VI's, for example V1, depends on all the other V's, so V2, V3,
Mm-hmm.
but it can't depend on itself.
It cannot depend on itself, and V2 and V3 has to be defined before.
And V2, V3 can't depend on V1.
No.
and 2.
Otherwise, it couldn't be
Otherwise, it would
defined
just be an
Yes.
advanced cycle.
Yes. So, for example, V1 can depend on some use. The use can be whatever, right? So the use are always. You see later that the use can be reduced to a set of use that are always independent of each other. But basically, you can create an order just depending on the V's, and the first V has to depend only on use.
Mhm.
Then the second V can depend on the first V and the other use, and so on.
So the assumption, we have to prove it in those cases.
No, you cannot. You don't need to prove. You have to assume
You have to assume it.
that the model was generated in some recursive system, from some recursive system. So this is kind of a philosophical question about what is a cycle in reality, because some people are kind of discussing cycles as a limitation of the data collection. Because if you have like a higher resolution in your data collection, you would always observe like the recursive way of generating. There's no instantaneous association in the end. There's always something. But then some other people, that's not with quantum mechanics and something like this. So I don't know. This is an assumption, right? So in some way, you have to assume that something comes first, and then comes the another. And if you are not able to collect if you are not able to detect which variable comes first than other, then you're going to create a confounding between them, and it's going to be. That's why some people are kind of explaining that these models that are with cycle are also part of the class of models that we can learn using the techniques here, because confounding could be a way of explaining this type of interaction between two variables that are just confounded because the resolution of the collection of the data was not fast enough.
Okay, I understand.
So so in the mathematical point of view, there's no cycles, and this is an assumption. You don't think more about it. It's more like it's unfortunate because there are many things that we know that, for example, in medicine, for example, you know that obesity and heart disease. You don't know like what comes first. Could be that the obesity is causing heart disease. It seems to be the common sense, but actually no one knows that. Could be that, or I don't know, high pressure. Could be that these other diseases are actually having a negative feedback, and actually hurting you by getting other problems and having more people more obese because of this. So when you collect data, you are collecting by looking at you like a photograph of you. Like, okay, you have all the symptoms, but you don't know which come first. So so that's a limitation I cannot explain.
I mean, also in nature you have a lot of cyclic systems where you have like maybe two components that react always to each other. So, for instance, if you have two populations, one of prey and one of hunters, like I don't know, dogs, wolves, and sheep, for instance, that these two populations have an effect on each other. So, if there are many sheep, you get more wolves over time, and then more wolves leads to fewer sheep again, and then that leads to fewer wolves again because they have less prey. And
yes. So the best way of analyzing this type of phenomena would be having time series data with like observing for many years what happened, but you don't know in the starting point what was going on as well. So anyways, and then this time series analysis always have some other assumptions behind it, like which means, for example, stationarity, which means that the starting point doesn't matter, or that because you can kind of switch, move away the original time point, and this wouldn't matter. So this is kind of intuition of stationarity. So if of course, if you had like resolution to observe like every second of nature, you would observe like exactly what comes first, and then you would explain everything. But this is impossible in practice. So the cycle, yes, they are there, and every time that you collect data, you have to assume some type of confounding like this. So I mean, and that's the theory as it is right now. So they assume no cycle. So that's not only about the pro framework. So the only other type of causality let me go to the next slide. I think I won't finish this lecture today, but I want to just to give this example because I think it's going to clarify something. So in statistics, you learn about structure equation model, probably, right? So who have heard about it? No, SEM, no one have heard it. So this is just a set of equations. So other names for it is structure latent factor analysis. Have you heard about it? No. Anyways, but this is the if you take some multivariate data analysis in statistics, you're going to see this type of model, which basically is like how can you do a multivariate analysis of so many variables at the same time. But usually we assume some parametric form for it. So yeah, there are some extensions. Probably if you were an expert on this, you would say, okay, there are no parametric structure equation models. There are, for example, others for non-normal distributions, but they are usually using other type of techniques. For example, you have to estimate the distribution of the arrows, or you have to do some non-parametric estimation of the curve. But in the end, you are going to have a function of this. You're estimating the function. And the idea of it is once you establish what's the system behind it, you can so basically you assume something, for example, linear functions, normal distribution. Other things that are common in the field is that the error terms here, the epsilons, they are all independent of each other, or anyways, there are other things that are not, but if they are independent of each other, this means that the covariance matrix, when the variables are Gaussians, right? So the covariance matrix are just the diagonal. If they are not independent of each other, you have to assume some structure for the covariance matrix. For example, they can have only ones out of the diagonal. I mean, you have to impose a few assumptions about this model so as the parameters are identifiable. Otherwise, you cannot identify the parameters. There are many solutions for it. And my conclusion here is that once you specify everything here, estimate a causal effect is really simple, because it's basically getting the parameter that you estimated here. For example, what would happen with the x if I change my x here to just small x, and then every time that I have an x, I fix this with a small x, and then I have the expected value of y given x. I have the model. I can just do some I can substitute the variable x to small x, and then just compute it. I have the distributions of u. I have everything. So causality from this is not really causality, because you're assuming a model. And if your model is wrong, everything is wrong, right? So the assumption behind it is that you basically you're assuming the solution. You're assuming that that's the order, the correct order of the variables, and then you can just get the causal effect by estimating parameters. I started asking about. So I moved to this. Someone asked me about something I forgot already, but we were discussing about cycles, and usually those assumptions are hard because if they are wrong, you're starting with the wrong foot, right? So basically, if your assumptions are wrong, you cannot trust on your analysis. So the idea behind the field is also to do the fewer assumptions as possible. So so in one hand, I really liked it that we talked a lot. So I really like these discussions, but I didn't finish the lecture. I don't know how tired you are. I can continue. But I think I would suppose to finish at 4, right? Or 4:30. Are you excited? I can continue. Okay. So yeah, that's the point. Like, because if I have the model, then that's computing effects of information from the model is really simple. So suppose that this is my model, my original model. And you can see here that x is a argument of the function of y, and x is not a function of y, right? So y is a function of x, and x is not a function of y. So x is a cause of y. But from this model, I can apply an intervention, and I have this post-interventional model, which is exactly the idea that I was explaining before. You just replace the whole equation of x with a small x, because this is what an intervention does. You go there and you change to a specific value. And the following equations, everything that goes after x, just receives the small x as parameter, because you fix it and everything that comes after is going to change. Everything that came before, for example, the uxi here, just go away, right? You don't need it anymore. And this model, you know that this is a completely different road than this other road where I performed the intervention. So in this left side here, which is called observational road, induces a probability distribution. So when I collect the data, I usually, like in a passive way, I'm collecting information that allow us to estimate the observational distribution. So this PV, remember V are my observed variables. So I can compute the probability of V, right, just from data about V. And this is going to come from this model M that has no intervention on it. It's the observational role. In the other side, and then from this type of probability distribution, I can compute those that you are used to do, right? So conditional probability of y given x if this is different than probability of y, then we tell that x is correlated to y. So there is a statistical association. And this allows us to do prediction, right? So this type of predictive models that you are used to do. In the other side, this model where we performed an intervention gives me, so the induced model from it, I can compute from it as well. So if I have the structural causal model, you can compute the probabilities. And this is in the question in the exercise, how to compute this. So you have to create first this by replacing the equation of x, and then compute the probability of v coming from this model, which is going to be exactly the probability of v given to x, the interventional distribution. And this actually can tell you if some variable is a cause of the other. Because if there is an association between x and y, if actually that's the definition, x is no longer a variable here, so that's why the definition is a bit different here. So if the probability of y coming from this model is the same as the probability of y coming from that model, this means that doing this intervention of fixing x didn't change my y. So it doesn't matter changing the x, y is going to keep the same, and that means that x is a cause of y. But if it's different, then x is a cause of y. So you see from the equation here that if I change x, I'm going to change the y, but it's because x is an argument of it. So from the structural causal model, it's trivial to compute causality, right? So do you know, sorry?
Sorry, for the previous slide, that means we need pre-interventional analysis to reach to this conclusion for causality for post-interventional. Because this one? This is not, I mean,
So if you have this model M, you have it. You have everything. You can do the intervention here. The intervention is just replacing the equation.
yes, I mean intervention is not independent of this pre-intervention. I mean to reach this conclusion that X is a cause of Y, we need P of Y, and P of Y coming from this pre-intervention.
Yes.
So we need to do this.
Yes.
One, this
Yes.
one.
Yes.
Also, Chris, what does it mean when it's an equal with a dot?
That's the notation for defined as.
Oh,
So yeah, sometimes people also do this. In computer science, people usually do this.
Okay.
In mathematics, people do this.
Okay.
They like to move the dots. Yes. So that's a good question, because when you do a randomized control trial, you don't have the interventional distribution. You have the probability of y given to x. The interventional distribution would be with the whole v. So for every variable in my system, I know what would be the effect on this variable. When I do a randomized control trial, I randomized one x, which is okay here. Usually we have a binary variable, so it's very limited. But the outcome, I mean, you can collect several features of it, but then yeah, you can have it. So, but you don't really so I think the limitation is about the x, right? So the limitation is not about the v, it's the limitation about the x. So with this, if you have the model, which is having this side here, you can compute the effect of x being of any variable, so don't need to be 1x. So you can manipulate the model as you want and get the interventional distribution of every variable there.
So from this model we can say it is a cause, or can we also say like to what degree?
So to what degree would be
like how much is it a cause?
Is a expectation maybe,
Yeah.
or like a function. So
Yes.
the expectation function. So from this you can compute it, right? So so you so you could change the x to several values here. So you can have like x, x0, x1, x2, x3, several x's, and see what's the effect on y. And then you can, for example, do some type of optimization. So which value of x is giving me the higher value of y. So you can see this type of things. Which, for example, the average treatment effect or average causal effect that I defined before, it's a difference between expectation of y given do x0 or 1 minus expectation of y given do x0. So I kind of choose two specific levels and computed the difference. If it's not binary, I would have to have a function of it, right? To every axis, I want to know what's happening, and then I have like the expectation function of it. But you can do it. Okay. So yeah, so from here, I want to give this distribution. So in statistics, probably you heard about the chain rule. Yeah. Okay. So from the chain rule, I can write the probability of V being like a product of the conditional probabilities. So I choose any order for my set of variables V, right? So if you're not following, please ask me. So you just choose any order for the set of variables V, and then you said that the joint distribution is the product of the variable given the previous ones, right? So that's the chain rule. And from the model, I can also apply the conditional independency. So from the model, you have the model, you can see which variable is independent of each other, and then you are going to be able to prove that this factorization holds. So basically, a variable is independent of everything else given the causes. Kind of obvious, right? So, and the causes can be observed ones, parents, and not observed ones. But this factorization holds. And when you are in the interventional distribution, so when you apply the do x, what happens is that the x is fixed, is no longer a random variable. So the conditional, the probability of x given the causes of x is now equals to 1, because I set x equals to x, so the probability of x being x is 1. So it's going to vanish. So I'm not going to have it. So when I have the interventional distribution, the probability of v given to x is written like this. And that's called truncated factorization, because it's just the same factorization as before, but I'm not considering the probability of x here, right? So this is conditional on x being equals to small x. So every time that the x appears in some of after the conditioning bar, I'm not going to use the x variable, I'm going to use the x value, right? So you can write. So from the structure causal model, you can compute this. And you could take like expectations, you can compute everything that you want from the structure causal model, right? So now I think I'm almost done. So the structure causal model is actually an encoder of the functional knowledge, right? So that's too much. So in practice, that's not available, or usually not available. So the question is, I gave the answer. So the question is it possible to identify effect of interventions, hypothetical interventions, from only observational data without fully specifying the structure causal model? So what I mean is a non-parametric way. So I want to not write the functions as a structure equation model as we do in statistics. I don't want to specify the probability of reuse. I don't want to write. I can give some information maybe, but not the full specification of the structure causal model. And the answer is yes, and this requires, so as I said from the pro-hierarchical theorem, the PHC pro-hierarchy theorem, we need some information that's in the layer 2, and this is going to be the structural knowledge. So structure means which variable depends on the other, but I don't need to specify the function that relates one variable to another. It's a lot already, so we're going to see how to relax this later, but in general, it's some parts of the structure of the model that's going to be necessary to actually do the inference of effects of intervention. Should I continue? Yeah. I need 5 minutes, or maybe 2. So I'm going to define causal diagram, then I'll stop. So this causal diagram is just necessary because of the exercises. So it's really simple. So basically, let's assume that so for now, we know that we don't want to know about the structural causal model, but we will need some type of information. And you see here that I'm not writing the functions, not even the probabilities of use, but I'm writing some type of order. So which variable depends on the other. And this actually induces a causal diagram in the following way. So we are going to add an edge, so it's a graph. So I'm going to consider only the variables on the set V, right? So I forget about the use. And I'm going to add an edge between Vi and Vj if Vi appears as an argument of the function of Vj. It's intuitive, right? So if that, for example, in my example, Z depends on a variable U. So I don't care about the U. I put the Z here, so it's not receiving any information from some observed variable. The X depends on Z, right? X is a function of Z. And Y is a function of X and Z. So Y has an edge coming from Z and from Y. Pretty simple. The U's are there. But the point is, these U's we can see later that they are all independent of each other, and for estimating effects of information, they are irrelevant. So it doesn't mean when I write this without the use, this doesn't mean that the system is deterministic. The use are there, there are randomness, but I'm just not showing the use here, right? That is another condition. That's when the use are correlated, and I don't have in this example, I don't have this. So if I don't have, so here I would add bidirected edge if the use are correlated or if the functions share some argument of u. I'm going to show an example right after this that has. But if I don't have, this is a condition that it's known in the field as that's called that the system is Markovian. So it's different from other Markovian that you have heard about, that only depends on the previous time if you're from statistics. So Markovian here in this sense means that all the confounders were measured. It's pretty strong. And many people are studying causality under this assumption and calling this as causal sufficiency. So if you read a paper and it's saying, oh, we assume causal sufficiency, this means that the use of the system are like here, where all the use are independent of each other, right? So all the use are independent of each other. So you don't have connections between the use. They are not correlated. They're completely independent of each other. And any variable that would be like the z here affecting both x and y, they are observed. So this is a scenario that's called Markovianity. So this is another example where this doesn't happen. So if you see here my equations, I have uxz in the function of z and uxz in the function of x. I also have uzy and uzy in both function of z and function of y. So they are shared information. So they are common causes, unobserved common causes of two of my observed variables. This forms confounding. So every time there is a common factor, this is confounding. Every time that's unobserved, it's unobserved confounding. And unobserved confounding is represented as dashed arrows. So in my example here, I have this. So if you follow here, z is just functions of the use, x is just functions of use, and y is function of x. So y is function of x. And my z, you see, there is even like this path connecting them. It's a collider, but the connection is through the variable's use, okay? So I'm showing the use so you can see what will happen with the dashed arrows. That's going to be this. So we are going to add a dashed arrow between vi and vj if the corresponding use, so the use that are part of the function of vi and the use of the functions of the part of the variable vj, they are either correlated or they are shared. In my case, it's just shared, but you could have correlation. So we add here x, z with a bidirected edge because there is a variable here that points to x and points to z.